Hi everyone! This video looks at a weak base titrated with a strong acid and will focus on the pH calculation at the equivalence point. If the titrant volume in the problem is more than 0 mils, then we have to set up a millimole table. The E row of our millimole table tells us where we are on the titration curve and guides us as to how to proceed with the pH calculation. There are many different generic notations for a weak base depending on the source. I choose to use a consistent notation of A- for a conjugate base. Some weak bases are not ions, and so I do recognize that it is possible the charge of A- may not align with the actual charge of the weak base. However, I do believe it's much easier to keep track of what's going on if we use the same generic notations consistently throughout all of these titration and equilibrium problems, rather than switching the notations back and forth. In this generic millimole table, we're looking at the E row. Here, we see that both A- and H+ are consumed. They have reacted stoichiometrically to produce the conjugate acid HA, which is the only thing in solution at this moment. Because both A- and H+ are 0, this puts the reaction progress at region 3 of the titration curve, which is the equivalence point. Only the conjugate acid HA is present, which we have generated through this titration reaction. We essentially have a pure solution of HA. It is important to recognize the result in this way because it helps us figure out what to do next. Because we have this pure solution of a weak acid, we now have to set up a mice table to evaluate the equilibrium of this weak acid. And this is how we'll eventually calculate the pH. Our millimole table gives us the amount of HA, but it is in millimoles. We have to remember to calculate the molarity of HA by taking the millimoles from the E row and dividing by the total volume. Then we can fill in the rest of the mice table. Moving forward, the process is identical to just starting with a solution of a weak acid. We will initially ignore the change in X, this minus X, and apply our assumption that X is small compared to the molarity of HA. After calculating X, we'll check this assumption. As a reminder, though, we cannot ignore a standalone X. Our next step is to set up the mass action expression for Ka, because we now have a weak acid that we created with the titration, and you will likely have to calculate Ka, but depending on the information given originally, there are different ways to do this. We'll solve for X, which is H+ molarity, and once we have H+, we can calculate the pH by taking the negative log of that value. There are a couple things to remember. First, we need to make sure that we are calculating the molarity of HA and that we don't just enter millimoles into the mice table. Also, we need to make sure that we are using the value of Ka and not Kb in the mass action expression. And two more things. The pH at the equivalence point of a weak base titration is not 7. This is the case only for strong acid or strong base titrations. The pH at this point will always be less than 7 because we created a solution of a weak acid, which by definition must be acidic. Also, this is not the case where pH equals pKa. That corresponds to the midpoint. For our example, the first thing we recognize is that we have more than 0 mils of titrant, which tells us that we need to set up a millimole table. The reaction at the top of our table is our weak base, A-, reacting with the titrant to form the conjugate acid, HA. The rows are ICE, initial change and equilibrium, and the units for this table are millimoles. We need to calculate millimoles, So we'll start by doing that for A minus. Our volume is 20.00 milliliters of solution times the molarity of the A minus, which is 0.02920 moles of A minus per liter of solution. Liters of solution will cancel, and we're left with milli and moles. Looking at our sig figs, we have 4 sig figs in the volume, 4 sig figs in the molarity, and so our millimoles will also be rounded to 4 sig figs. Doing the math, 20.00 times 0.02920 rounded to 4 sig figs gives us 0.5840 millimoles of A minus. Moving on to the titrant, we have 14.60 milliliters of solution times the molarity of the titrant, which is 0.04000 moles of H plus per liter of solution. Liters of solution will cancel here, and we'll be left with milli and moles. We have 4 sig figs in our volume, 4 sig figs in our molarity, and so our millimoles will also be rounded to 4 sig figs. Doing the math, we have 14.60 times 0.04000 rounded to 4 sig figs gives us 0.5840 millimoles of H plus. We can now complete the millimole table. So our A minus 0.5840, our H plus 0.5840, and HA is 0. So we subtract 0.5840 from A minus and from H plus, and we add that value, 0.5840, to HA. A minus goes to 0, H plus goes to 0, and HA goes to 0.5840. Evaluating the E row, because both reactants, A minus and H plus, went to 0, this tells us that we're at the equivalence point. Before we set up our mice table, we have a couple of calculations that we need to do. The first one is to calculate the molarity of HA, and we get that from our millimoles in the E row, 0.5840 millimoles of HA, divided by the total volume, which will be 20.00 plus 14.60 milliliters. The millis will cancel, and we'll be left with moles over liters, which is molarity. Looking at our sig figs, we have 4 sig figs in the numerator. We have 4 sig figs in the denominator, so our molarity will also be rounded to 4 sig figs. Doing the calculation, 0.5840 divided by 34.60, rounded to 4 sig figs gives us 0.01688 molar HA. The other calculation we need is to get Ka. We're given Kb in the problem. As a reminder, Ka times Kb equals Kw, which is 1.0 times 10 to the negative 14. Rearranging this equation to solve for Ka, Ka equals 1.0 times 10 to the negative 14 divided by Kb. So that will be 1.0 times 10 to the negative 14 divided by 1.7 times 10 to the negative 5. Both values have 2 sig figs, so our calculated Ka will also have 2 sig figs. Doing the math, 1.0 times 10 to the negative 14 divided by 1.7 times 10 to the negative 5 gives us a Ka of 5.9 times 10 to the negative 10. Now we can set up our mice table. So our mice table is for a weak acid. The equilibrium at the top will be Ha dissociating to form H plus A minus. Our rows are I, C, E, initial change and equilibrium, and our units here are molarity. So we just did the calculation to calculate the molarity of HA, and that was 0.01688 molar. H plus starts at 0, and A minus also starts at 0. The change row is minus X for HA, plus X for H plus, and plus X for A minus. The E row becomes 0.01688 minus X for HA, and X for H plus and A minus. Our mass action expression is for Ka. Ka equals H plus times A minus divided by HA. So we can plug in the values, rearrange, and solve for X. We calculated Ka a little bit ago. That was 5.9 times 10 to the negative 10 equals H plus, which is X, times A minus, which is also X, divided by HA, which is 0.01688, because we're ignoring the change in X momentarily. Cross multiplying, we end up with 5.9 times 10 to the negative 10 times 0.01688 equals X squared. And we can take the square root of each side to give us X. Taking a look at our sig figs before we do that calculation, we have 2 sig figs in Ka, 4 sig figs in the molarity, so when we solve for X, we'll round it to 2 sig figs. So doing the math, 5.9 times 10 to the negative 10 times 0.01688, and taking the square root of that, rounded to 2 sig figs, gives us 3.2 times 10 to the negative 6. Looking at our mice table, we see that X has units of molarity and it corresponds to H plus. Before we calculate the pH, we need to check that our assumption to ignore the change in X was a valid assumption. So we check this by taking the X that we calculated, 3.2 times 10 to the negative 6 molar, divided by the HA molarity, 0.01688 molar, times 100. The units of molarity will cancel, and after we multiply by 100, we'll be left with units of percent. The sig figs in the numerator are 2 sig figs. We have 4 sig figs in the denominator, and the 100 is exact. So when we do this calculation to get this percentage, we'll round it to 2 sig figs. So doing the math, 3.2 times 10 to the negative 6 divided by 0.01688 times 100 gives us 0.019%. And our threshold is 5%. So because this is less than 5%, our assumption is valid. We have one more step, and that's to calculate pH. pH equals the negative log of the H. So negative log of 3.2 times 10 to the negative 6. We have 2 sig figs in our log term, which means we have to round to 2 decimal places in our result. So taking the negative log of 3.2 times 10 to the negative 6, rounded to 2 decimal places, gives us a pH of 5.49.